Let's do the direction where we assume that f is 1 to 1 and onto. Okay, so we assume it's 1 to 1 and onto, and we want to prove that an inverse exists. So let's try to define this inverse, okay? So we need to define g going from y to x. And we have to define it so that it's a function, and then it has to undo f, and f has to undo g. How do we define it? So we take a y, so start with a y that's in y, okay? Well, because f is onto, there exists an x, okay, such that y is output from that x. So for some x, okay, because f is onto. Now, because f is 1 to 1, this x is unique. Okay. So there's no other x for which f of x equals y. There's only one x. Okay. So therefore, the way we define the function g, therefore, we can define g of y to equal x. Okay. So there's only one x for which f of x equals y, and there's that one x for every y. So we can define that to be the output of y under g. That's the function. So now we just have to check that g undoes f and f undoes g. Okay. Well, if you look at f undoing g, it looks like this. Okay, and we're meant to show that that's equal to y. But what is that equal to? Well, that's just f of the left-hand side here. So it must be equal to the f of the right-hand side. But f of x is by definition y. Okay. So f certainly undoes g. Does g undo f? So if you have an x, and you take the f of it, then you take the g of that, you get back to x. Well, you do, because we define g that way, right? So this x is unique, that gives f of x. So g is defined to always get back that original x. So g also undoes f. Okay, so that's one direction of the claim.